Our final talk for today is Zachary Henkel, who's going to give us an update on adopting header units in Microsoft Word. Take it away, Zach.
Thanks very much, Sai. Happy to be with all of you here today. Thank you if you're attending live or if you're watching this after the fact. I'm Zachary Henkel. I'm an engineer on Microsoft's core architecture team. So now you know why Sai selected me to be here today. They wanted one more cat to get on screen. I'll be giving this progress report on adopting header units in Word. It's a topic that I've talked about a couple times before. There's a blog, series of blogs that I've done with Cameron to Camera on the compiler team, and also who is joining us in chat today. If you have questions, Cameron can try to get them answered while I'm presenting. Hopefully we can get those links up on screen if you want to. Oh, there they are, perfect. If you'd like to dive deeper in them, it's not required that you've read them, it's just if you want some background later on. I'm not going to keep you in suspense waiting for the performance numbers that we've been promising for a long time. After adopting header units in Word, the worst case that we found is approximately a 1% regression in compilation speed. The best case is 21% improvement. And I'll spend the rest of the time talking about the scenarios that produce these results. Before we get into that, though, I want to give a little bit of background. So what's the problem that we're trying to solve by adopting header units? Of course, the answer is we want to reduce the amount of time developers spend sword fighting. I'm sure everyone's seen this before. As C++ developers, we're always on the lookout for tools and techniques that will improve build speed. In Office today, the biggest gains from developers only building a portion of the full repository. We call that partial builds internally. So Word developer is only required to build the code that makes up Word and some of its closely related libraries. The other big improvement is employing a precompiled header. And as I just noticed Cameron said, precompiled headers are a 30-year-old technology. So keep that in mind as we're talking about header units, which have only been on the scene for 5 years. There are still a lot of opportunities we're uncovering to continue improving and optimizing. So what are header units? The short version is that header units are a binary representation of a header file. At least with the MSVC compiler, it'll produce the same format as named modules, IFC format. But unlike named modules, it includes both, will include macro information that can be both a pro and a con. The important thing for Office, though, is that they can be adopted with minimal source file changes because we compile for all of the Office platforms out of a single monorepo. I guess I'm getting ahead of myself. That's the next slide. But we needed to be able to do this without having to have a lot of invasive changes. So there's a translate include flag for the MSVC compiler. And then there's an IFC map, which can help you build up a large number of these translate includes. Both of those are available on the Learn Microsoft site on the compiler documentation. So this is kind of under the covers. What that translate include winds up doing is turning the pound include into an import directive. So the short version of what Microsoft is, give you a little bit of background here. If you want to see a lot more detail, I have a presentation that I gave at CppCon 2022. That's up on YouTube. Again, I'll go through just the kind of the key points right here. It's about 100 million lines of native code. We compile for 3 major platforms, Windows, Apple, and Android. And because of that, we have 2 compilers, MSVC for Windows and Clang for Apple and Android. And of course, those are not exactly the same Clang either because the vendors take snapshots at different times. They do things to cherry pick fixes or add platform-specific things. One note, I'm probably going to slip up during this presentation and talk about liblets. Again, there's a ton of that in the CppCon video that I gave earlier, but you can easily think of them for the purposes of this talk as kind of nicely packaged libraries that are shared code within Office. So what are the conditions that we set when we started the experiment? So like I mentioned when I was talking about the attractiveness of header units, we couldn't have intrusive source file changes. I'm not saying that no source file changes were required. For the most part, we had found very virtuous changes that needed to be done. Um, Creating a header unit would force the file to be compiled in isolation, and we'd find tons of cases where headers would be missing all their required includes, either because they were provided by a downstream precompiled header, or you're just getting lucky because any consumer's include block would just happen to be in the right order that was taking care of them for you. Any amount of build logic and command line changes were going to be okay. A lot of our build unit logic is distinctly per platform. So when we were authoring header unit support only for Windows at this time, it didn't really impose a large burden on the other platforms. And then it was easy to mask the changes required for staged adoption. It could all just get hidden in the build logic itself. So what was the big hypothesis when we got started? Header units would demonstrably improve inner loop build speed for engineers working on Microsoft Word. So let's pick that apart a little bit. The focus is specifically on inner loop speed. How fast can a developer edit code on their local box, rebuild the relevant portions of Word, and get to validating their change? And a bit of foreshadowing, I'd like to note that inner loop builds are almost always debug builds. Word was our first target because of one of the things that's required for header units, and this is something that was called out in the blog post. You need to have uniform build arguments. It's going to lock in all of the compiler flags and preprocessor definitions as you create a header unit. So you need to make sure that any projects or code that would be consuming them agrees with what was set when you were creating them. Word already had a high level of consistency with a set of those preprocessor definitions and compiler flags, and the low-level libraries that became our first header units. Word wasn't the only candidate application, and hopefully I can talk about some other projects where header units can be adopted in a future presentation or blog post. So this is what Word's physical code layout, at least as it relates to what we'll be talking about with header units. There are two precompiled headers that the code can select between. MinPCH is extremely lightweight. It contains the standard library, Windows.h, of course, some common Word internal helpers, and a very small subset of upstream functionality. Those Office headers that are included in here are limited to very low-level things, some common data structures, platform code, nothing customer-facing. If you count all the transitive includes inside of MinPCH, it's only about 250 files. It's also not particularly widely used inside of Word. Only about 2% of the files choose this as their PCH. Word shared is the complete opposite extreme. It captures nearly every upstream header, with only some minimal holdbacks for test headers that try to do clever things with macros and things like that. It contains about 2,500 files if you're counting all the transitive includes. Makes Word shared a pretty challenging test for header units just because of the breadth of code that's being compiled there. And the other thing in terms of compilation speed is that the Word engineers have spent a lot of time looking with build insights to make sure that the PCH has maximum effectiveness. So how does this diagram change after we adopt header units? We create a header unit for the standard library, and as I mentioned before, some low-level libraries that are already header units. Combine them with the existing contents of MinPCH or Word shared, and then create one single header unit out of each. There are no changes. We just took what was in there and converted it to become a header unit. The existing includes get imported to an import statement for the case of like the standard library and the low-level ones via translate include, and that's it. And then also where you would normally have like pound include MinPCH or pound include word shared.h, those will also be translated via translate include into an import statement. So for the experiment design, we use Build Excel as our build engine and found several of its capabilities well suited to setting up benchmarks. The general flow of a test was as follows. Perform a full build of Word. This is done so that all the dependencies required just to invoke the compiler are created successfully on disk. Choose whether it's going to be a PCH or header unit test. Then I would disable build caching, run all the compiler invocations, and do it 7 times. It's easy to do with Build Excel. You can isolate just things that are labeled, and we label all of our compilations. I did 7 times so I could throw out the highest and the lowest measurements in any given set. And then I gathered just the CPU time spent by the compiler. One of the things that we noticed from the start of the experiment, though, is that the measurements were going to be very noisy, because if they take a long time to run, anything could be happening on that box. Our IT could force a scan. The scheduler, which isn't deterministic, would make a particularly good choice to favor header units or precompiled headers. So we needed to do this repeatedly. So I repeated it every night on 3 unique boxes for 3 weeks. I wound up with a data set of 15 different invocations times 3, so 45 across all of these. Here's the equipment that I use for testing, since I mentioned there was 3 different boxes. The most powerful of these, Office, we affectionately call them build the world machines. They're for developers who are working on things that are going to be across all of Office. It's a single CPU, 64 threads, roughly 4 gigahertz peak clock, 256 gigs of RAM. There's a boot SSD in there, an NVMe SSD, and then there are multiple SSD data drives set up with software RAID. Specifically, this is Microsoft storage spaces in simple mode. Simple is like RAID 0, so you have speed, but there's no redundancy. The physical workstation reflects what a developer working on an application team like Word would have for their primary development workstation. 32 threads, again, about a 4 gigahertz peak clock, 128 gigs of RAM, and a similar setup to the BTW. Just you have fewer RAID drives. I think these are, for most of them, there are 2 or 3. The BTW has 6 of them. And then the final class of machine I test against is Microsoft DevBox. This is actually a publicly available product that Microsoft sells. It's a virtual machine running in Azure. The VM provides 16 threads, 3.5 gigahertz peak clock speed, 64 gigs of RAM. And in this case, there's only a single drive from both the OS and source. All the Microsoft Dev boxes run on Azure Premium SSDs, the P30 SKU. There are other options, but these are the ones that are available in Office. So here's what the data looks like for building all of Word. Word's roughly 6,000 files. The BTW did well, and you can see there's error bars on some of these where you can see a little bit of the noise, or it kind of reflects the noise that's inside of here. The physical workstation was just about even. This is like, I think, negative 0.1%. The MDB machine shows the measurable regression, kind of just about 1%. So if you notice, or if you call back to the second slide, this is what I mentioned for the worst performance. This is it right here on the MDB machine compiling all of Word. But this isn't the best result that I talked about. That's because recompiling every file in Word isn't the typical experience for a developer. Typically, you'd be working on an individual feature. You'd be making a bug fix, small change. You just need to recompile a handful of files and then be ready to go. To do a better job simulating those workflows, I asked for some of the most active investment areas in Word and found 2 good candidates to measure. So the first of these, I'm just going to call folder A. It consists of around 300 files. With this, you can see the BTW pulls way ahead. This is about 11%. The typical developer box and the VM gain both show a nice gain, above or below 3%. And then the other area that I was told about, I'm going to just call folder B. This is 200 files. And then this is where we get that largest improvement that I talked about. This is over 20% on the BTW. And then the physical workstation starts to really pull ahead about 9%. And then the VM, a small but noticeable improvement at 1.3%. What does this all mean? So one thing you could say, and I'm sure all the developers in Office would be happy if this was the takeaway, is that all developers should have server class hardware. Unfortunately, that's not particularly realistic, so we have to dig a little bit deeper. So what's going on? There must be some kind of common factor among these three machines that explains why we see the difference in performance. Was it the CPU? Well, I don't think so. Both the physical machine and the BTW had very similar CPUs, but different performance. Peak clock was off by 100 megahertz, but there was the same vendor, same architecture, same CPU generation. So I'm not going to say it's the CPU. What about the RAM? Well, we tried the physical development machine with some results that I didn't show because ultimately they didn't actually show any measurable difference versus what you actually were getting with kind of the standard amount of RAM in that machine. What about the storage? Well, this is where I think it is for two reasons. First is that we did some internal tests because I just kind of asked for some off-the-shelf hardware to start doing my benchmarks with. And one of the things that we noticed was a difference between hardware RAID and software RAID, which is why I had called it out in the earlier slide talking about what the machines were that we used. The hardware vendor sort of has, if you look around on the internet, is known for not having good hardware performance. And so switching from using their low quality hardware RAID to the software RAID, we got a 40% speed up once you were switching from one to the other. Plus, I was running, some artificial benchmarking software that just does kind of storage benchmarkings, and it was significantly higher results using with that benchmarking software. 2.5 times better for read perf, 3.2% better on write perf. So clearly improving the storage system helped with this as well. But why is storage speed what is dominating? So I gave you a clue earlier. So after some investigation, we noticed that debugging information was causing additional writes under header units that weren't there under the PCH. Oops, sorry. So how much extra information are we talking about? We looked at the size of the object files on disk, and they were a lot bigger. So the sum of all of the object files created for Word was 22% larger consuming header units versus consuming a PCH. The median increase was 25%, and then the largest was almost 9,000% larger under header units. That's not a typo. So I have to thank Cavern and Gabby, who I see quite active in chat over on my other screen here, for helping me investigate this from the compiler side. The biggest offender we found was a pair of enormous enums being written into the object files. And when I say enormous, one of them was 10,000 entries, the other was 30,000 entries. So don't do that, friends. One of them was an enum containing all of the command IDs for every single app in Office. The other one was data points for doing performance, correlating performance data. So yeah, it was entirely too much. The long-term plan will be to teach the toolchain how to reference this information directly from the IFC instead of having to duplicate it into each object file. The short-term plan was the very high-tech solution of simply excluding the two headers that included this information from the PCH. Here's what it looks like after we did so. The total file increase goes down to 18%, median down to 22%, and then the largest is only like 1,700% bigger. Still not where we want it to be, but it did help quite a bit. It does emphasize that there's more work to be done by the compiler, and it can't only be solved by editing Office headers. I'd also then like to call out that all of the data that I showed in the charts above, that was after editing the files to remove these enormous enums. One of the other things that I'd like to call out here is that this also explains the differences between folder A and folder B. Folder B actually wrote 14% more data than folder A, which is why you see a larger performance increase across all the boxes, or I guess not all of the boxes, but I guess the more resource constrained boxes with that test set. So that's enough of the unfortunate news. How about some good news? Beyond build speed, header units have additional advantages. First is that they're portable. So precompiled headers produced by MSVC must be created locally in order for them to successfully be consumed. Header units don't have this limitation. It would be possible to employ that partial technique that I talked about earlier that we use in Office. You could have a project upstream of Word that created the two precompiled headers. And then any developer would simply be able to have the contents brought down from the build lab, from our cloud infrastructure, and then skip having to create them at all. The second is that IFC is amenable to tooling. We have a specification for this. We provide an SDK for it. Cameron had a pre-conference video for this if you'd like to see more about it. And then finally, and thanks for sharing that link. The header units and modules are considerably smaller than a PCH. How much smaller? 90 to 95%. I've been gathering data on this for quite a while, and every time I see these numbers, I still wind up being shocked. You might point out that it's not fair to do an apples to apples comparison between the final header units, like the ones that are in Word, and a PCH, because the Word header units have references to upstream header units. They compose very nicely. You don't have to duplicate information. It just knows how to go look it up in a required dependent IFC. So that's fine. I agree with you. Let's bring up the numbers if you add up everything upstream as well. I think this is still pretty good at 77 and 88%. So what do we have to do to take this further and keep realizing these gains? So unfortunately, there's an incremental linker bug that we uncovered. The fix is pending. It'll be in the very next release of the 17.8 branch in May. Unfortunately, if incremental linking fails, it falls back to do a full link, and that one's just destroying your kind of inner loop build speed. So we had to pause the experiment for now. If you're going to be adopting 17.10, it's available right away from the RTM version here. Then the other is the big call out here, which is to reuse the debugging information from the IFC. This is more invasive than some of the other things that some of the other requests that we've had to the compiler team for fixes and improvements, because it requires the entire tool chain to work together on this. The linker will have to be updated. The PDB writer will have to be updated for this. And so unfortunately, because of that, this is work that's underway, but we don't have any date to share today about when it'll be available. We'll be sure to talk very loudly about this when it's ready to go. And then on the Office side, what do we have to do? As I mentioned earlier, we have additional opportunities to test header unit consumption in some of these end applications beyond Word. We'd like to start this in the very near future. At the same time, we want to continue making low-level libraries into header units. Before doing so, we have to remove our equivalent of like a root inc folder. It's a collection of headers that don't share a single logical responsibility. Once these headers can find a new home, their component libraries can have a header unit created for them. And then if that's unlocked, we can create the shared precomp that powers so much of our shared code as a header unit. And that inflection point will open the floodgates to making more header units. As I called out in the blog post and have talked about earlier, the biggest thing you have to do in order to be able to see these gains is not ask the compiler to do extra work deduplicating information for you. And that's why you have to take this kind of bottom-up approach to make sure that you don't textually include things into multiple header units, because that's just going to waste the compiler's time and thus your time. And then finally, we have to continue striving for consistent build flags. We've done a lot of the work to do kind of internal marking to make sure that we understand where we have disagreements. And it's just a matter of then doing the actual work to make sure that all of those things are consistent, and then additional projects can be incorporate header units. And of course, I'll close with the same motto that we've had since we first started talking about this. We want to build all the header units. And I hope to continue sharing the details of this journey with you until all of the header units are built in Office. Thank you.
Great, thanks so much. It's really cool to see all of the numbers on that and see that even adopting header units and not full name modules gets you a fairly substantial speed up to your inner loop. That's really exciting.
Yep, thanks so much, Simon.
Yeah, all right. See you later, Zach. Okay, and that brings us to a close of the day. Thank you, everyone that has joined. If you have any more questions, feel free to drop them in chat. I believe we can maybe still answer them. I cannot remember. Or find us on Twitter or email. We do have a survey, which would be really great if you can fill it in to let us know what we can do differently next year. You should see the QR code on your screens now. And on the run-up to the conference, we published a whole bunch of pre-recorded videos. So please go and check those out as well. There's like 15 or 16 videos. The link is on the screen right now. And they're on a whole host of C++ topics. The videos for the sessions you saw today will all be up on YouTube, so you can watch them again or reference them. And thanks very much, everyone, for joining us, and see you next year.